Hello, YouTube. Welcome to part B. It's been all of 2 seconds for me. So we've got a chain with a length L and a mass of M that's sliding off a table. We're trying to figure out how fast the chain will be moving when it leaves the table. So to do this one, what we're going to do is draw out our problem and solve from there. So the thing that's weird about this is that this is basically a system with a varying force. We've got our chain that's just barely lined up on a table. I need to change that first question. The chain starts infinitely close to being on the table and is starting from rest. So we've got this chain of length L. The total mass of the chain is M. What I'm going to represent this as is some distance that the chain has slid. We'll call that X. That's going to be this here. If I take the amount that's still on the table, the amount that's still on the table is going to be L minus X. The mass that is off of the table is going to be equal to the linear mass density, meaning just how much mass there is per unit of length. We can basically say that the whole thing for a length of L has a mass of M. So if I want to find the mass of a certain length, that will need to be equal to the mass of that certain length divided by that certain length. So if I want to find the mass of the section hanging off the table, it'll equal the same ratio as long as that chain is of a uniform, like there's not half of the chain is thicker than the other half. This will be that same ratio. So what we can do here is that the amount that this thing is getting pulled down, the amount of net force pulling this chain off the table is going to be equal to the mass that's hanging off the table times G. For a system, that means that if we take mH times G, that'll need to equal the total mass of the chain times the acceleration of the chain. mH is a little bit weird though. If we multiply each side by x, we'll get that xm over L is equal to mH. If I take this and plug it in over here, it'll give me that m over L times x times g is equal to ma. Dividing each side by m, we have a situation like the one we had before. G over L times x is equal to our acceleration. To solve this, this is actually just like our last thing, except it's got G over L instead of a random constant. Our specific constant is that if we take gravity and we divide it by the length of the chain, multiply that by the amount of chain that's slid off of the table, that'll give us our acceleration with respect to position, and specifically how far it's slid off the table. What we want to do for this one is the same thing that I was just talking about in the last part. We're going to say that our acceleration is equal to the derivative of velocity with respect to time. And that that's equal to the derivative of velocity with respect to x times the derivative of x with respect to time, which is velocity. When we've done that, what we'll wind up with is that G over L times x is equal to dv v over dx. Multiply each side by dx, integrate, and we're done. Well, we're not quite done. Now we need to integrate this over the terms of our equation. In this case, we need to integrate it from, and I'm actually going to bring it over here and rewrite it. We've got g over L x dx equals v dv. We need to integrate from 0 until we get to the total length of L for the position. And for the velocity, we need to integrate from 0 to our final velocity that we still don't know yet. Over here, what we'll get is that g over L times 1/2, so g over 2L, x squared evaluated from 0 to L. And over here, we'll get v squared times 1/2 evaluated from 0 to vx. Now the zeros on both of those are just going to be 0, thankfully, and we can just plug in the L here. We can also go ahead real quick and get rid of the halves. When we do that, we'll actually just get g L squared over L, which makes the L's drop, is equal to v squared. Square root both sides, and we're done. Our velocity at the end will be equal to the square root of gravity times the length of the chain. And that's it. Hopefully that's not too bad. It's just sort of taking that last one and putting it into practice. Hope you have a great day, and goodbye, YouTube.